Hi everybody. It's been a quiet office hour, so I figured I would just record an example, record a video to go over the example that we didn't quite finish at the end of today's class. Then I figured you could kind of watch it at your own convenience over the next couple of days. So just to review, the idea that we're working with is I wanted to simulate collecting multiple different confidence intervals associated to different samples from a normal population. And I wanted to look at our confidence level in terms of a simulation size, so essentially a success rate. So if we collect 3,000 different confidence intervals generated from different sample means, how many of those confidence intervals actually contained our original population mean value? So in class, we already did this part, but I'll just start from the beginning because I think it's worth repeating. Inside of our let me just pull up where we're working. So this is inside of our week 6 materials, our stuff. And in the data value, inside of our data folder, there's a CSV called population data. And if we pull in that with our first command here, we can take a look at this population data. It's a data frame. It has one variable with whose name is X, and it contains a bunch of different measurements coming from our population. So in class, I looked at the histogram of this population data, and you can see it has a very nice bell-shaped curve, which is a rough way to sort of verify the assumption that we're sampling, right? We're essentially going to be taking samples from this large population. We're sampling from a normally distributed random variable, okay? And we actually, since we have all of the data, we can consider what the actual population mean is. So at the population level, it's a 99.682. Now what we're going to try to do is look at samples from this population data. So for example, if I took sample population data X, so this is all of my population data, and I sample, let's say, 30 different observations, I'll collect 30 random observations from this much larger data set of population data, $X. Okay? So the idea here is I want to create a confidence interval based on these random samples of size 30. And I want to see how often, if I repeat this process over and over and over, how many of the random confidence intervals I generate actually end up giving me an interval where my true population mean, this 99.682, actually falls. Okay? Now in the real world, as researchers, we're typically just selecting one sample. We go out and collect our data. And we collect the sample from a large population, just like we're doing in this case. And we use that to estimate mu using a confidence interval, our population mean. But in R, we can actually simulate this process. So it's as if we sample, consider, say, let's 3,000 different samples, look at their means and the confidence intervals associated to those sample means. And we can see how many of the confidence intervals we generate actually end up overlapping the true population mean. All right, so here's what we did. Or what I'm going to do. For convenience, we're just going to define this quick function get x bar, so get sample mean. All it's going to do is start with my population information. It's going to use the sample function to select a specified number of, or to sample a specified number of observations from that larger data set. And I'm going to save that under the name samp. And then I want my function to return the sample mean. So I'm going to take those n observations and take the mean of them. So when I run this, I now have my xbar function saved into my workspace. And now, like we've done before, I'm just going to use a for loop to collect 3,000 different sample mean observations taken from that larger population. So I start by initiating a nice vector, possible sample means. I create 3,000 spaces for it, and now I'm going to loop through from I1 to 3,000. I'm going to overwrite my ith component of this storage vector with a random sample mean where the sample size is from 30. Okay? And again, we're taking a random collection from this population data, right? So from this vector of population scores. Right? So we're sampling size 30, we're taking the mean, and we're storing that particular observed value of x bar inside of this vector. So let's run these two pieces. And we can see here we have essentially just a vector of these different sample means we got from randomly selecting 30 scores from that larger population. The total length of this is, of course, 3,000, so we have 3,000 different observations. Okay? So as I started to mention during class, we're going to start to store most of our information inside of data frames. In fact, R is really written to work with a data frame approach to data analysis. So the code below here, maybe I'll make this a little easier to see. To create a data frame, we're just going to use this data frame command. And the input it takes, you choose a column name, and then you're going to input a vector of actual data. And what it'll do is it'll create a data frame where this is at the top, and then the scores that you're trying to record are listed off in this vector here. All right, so we're going to create this data frame called CIS. CI are capitals, it's initializing confidence interval, and S is pluralizing it, so it's short for confidence intervals, essentially. All right, what we want to do is add a variable called sample means, and the data that we want inside of that column will be the data we just collected, these possible sample means up here. All right, so here's our code for doing this. We define the name of our data frame. We're going to assign it a data frame object. Here's the name of our column, sample means, and here's the data we want to put into that column. So when I run this code, it creates the data frame, and now if I sneak a peek at this data frame I've currently created, there's our title, sample means, and here are all of our observations. This was coming from our vector up here, and you can kind of go line by line and see that they're all the same. Oh, actually, too many to check, so just trust me that they're the same and in the appropriate order. Okay? All right. So the next thing we wanted to do, so for each random sample mean that we collect, we're going to associate a confidence interval. Okay? Now it turns out when you're doing a confidence interval using this normal approach, the margin of error, so long as you keep your confidence level, will be the same because our standard deviation at the population level isn't changing, and we're keeping a consistent sample size of 30. So all of the things that you modified to determine your margin of error in this case are remaining constant. Right? We're going to assume that the population standard deviation was provided to us. This is one of the assumptions we talked about in class today. And that standard deviation in this case is equal to 22. This is what I use to generate the data. Okay, so let's use our margin of error. And remember the general form that it takes. We have our critical value, which we get out of a Q norm. I'm going to use a 95% confidence level, so my alpha value is 5%. I cut that in half. I do 1 minus alpha over 2, Q norm, and then I'm collecting a z-score, so my mean is 0 and my standard deviation is 1. So this is my z-critical value. Here's the assumed standard deviation at the population level, which is 22. And then, of course, we divide out by the square root of our sample size. All right, so here's our margin of error. It ends up being 5.477, etc. And now what we want to do is create the lower and upper bounds for our confidence intervals. Okay? We're going to do this by adding information to our data frame. We can add a column by calling the data frame and then using a $ and creating a new name. So for right now, right, before I run that code above, the CI's data frame only has one column. If I want to create a new column and I want its name to be, say, lower bound, I'm going to start my line by typing my data frame name, a $, and then my new column. And what I'll do is I'll assign to this new column the values that I want. This will essentially take the sample means that are currently sitting in that first column, and to create the lower bounds, I'm going to subtract this margin of error. I'm going to subtract 5.477. All right, so as I run this code, oops, forgot to run this up here, ME is saved. Now as I run this code, you'll notice that looking into CIs at this point, I have my sample means and the lower bound to the associated confidence interval. Okay? Now, if at this point you're looking and you're saying, oh, my sample means and all my lower bounds are different, that's fine because when you generated your random samples, they're different than mine. All right? But they should look roughly the same in scale. Okay? All right, so what I want you to do is pause the video at this point and try adding the upper bounds and see if you do the same thing as I do in a second. All right, so pause the video, give it a shot, and then you can hit play. All right, so adding the upper bounds, we call our data frame. We choose upper bound maybe as our column name. If you choose something slightly different, it's not a big deal. And now what we're going to do is put in, from our sample means, we want to add the margin of error, and this should determine all of our upper bounds row by row. So when we run this and then we check the contents of our data frame, we should now see 3 columns. We have the sample mean. These were row by row randomly generated from a unique 30 sample from our population, or sample of size 30 from our population. From that, we subtracted our margin of error to get the lower bound of our confidence interval, and we added the margin of error to get the upper bound of our confidence interval. So row by row, we have our random confidence interval generated by this sampling process. Okay? And you can see that at least for the first 4, they truly are random intervals, right? Where they start and where they stop varies depending on the sample that we collected. But you can see that at least with the first 4, we were successful in capturing the actual population mean. Just as a quick reminder, the population mean was 99.682. And so the first, however many of this are, 6 or 7, all have that population mean inside of them. But you'll notice that this one here, which I guess is the 7th, does not contain that. So sometimes you're going to randomly generate an interval that misses the mark in a sense. It does not contain that population mean. Okay? So what are we going to do with this? Now we want to check essentially what's our success rate. So what I want to do is go through my confidence interval data frame, and I want to check row by row, is my population mean in between the lower and the upper bounds? And the way we're going to do this is by adding a logical vector that essentially determines whether 100, actually I'm going to use 99.682, is the true population mean. Does it fall between the true population mean, does this thing fall between the lower and upper bounds on a row by row basis? All right? We've seen logical vectors before, but what we haven't done possibly is save them under a name. So I'll show you how to do this. Once again, the mean for our population data is the 99.682. So this is what we're checking is in between our lower and upper bounds. We'll do this in 2 steps. The first takes each one of the lower bounds row by row and compares it against the 99.682. And so what this is going to do is check for each row, is the lower bound for that given row below the 99.682? And it's going to give us a vector of trues and falses. Okay? And if we take a look at that vector, we can see that it's true for everything up until 21, 22, 23, 24, 25, 26, 27, 28. The 28th one is going to have a case where the lower bound is actually above our population mean. So the confidence interval in this case is going to miss. Right? We also want to check, is it underneath the upper bound? So we can write a very similar logic vector. Let's save it under the name logic vec2. We take now the upper bound data and we compare it against the population mean of 99.682. We can run that and take a look at this, right? False, 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 or true, 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 except for there was our 7th one. Remember that confidence interval undershot our population mean. And we can see this now. The upper bound was actually not bigger than our actual population mean. So if the population mean is in between the lower and upper bounds on a row by row basis, right, we would have the row for logic vector 1 and the row for logic vector 2 both being true. So essentially what we want is a way to combine these logic vectors where if they're both true, we return a true, but if one of them is not true, we return a false. So for those of you who have taken mathematical reasoning, right, this is essentially looking at an AND logical operator. And in R, we can do this with an ampersand. All right, so this is a Shift 7 on your keyboard. All right, so basically what an AND does is it looks at 2 logical values and returns another logical value based on those values. So a quick way to check this, I just put together this little truth table. The AND operator only is going to return true if both of the 2 pieces are true. So you can see we have 4 different comparisons. It's only true and true that returns true. All the other ones give false. Okay? Using the AND operator on vectors of the same length, we'll compare things component-wise, so essentially row by row. So when we run logic vec1 ampersand logic vec2, we get essentially a logical vector of trues and falses, where we'll see falses if either logic vec1 or logic vec2 happen to have a false inside of it. All right, so this very nicely looks at whether or not, this is now looking at essentially true or false, is my population mean inside the interval that I generated for my confidence interval. All right, so let's store this logical vector. We can use just the AND operator. Let's store it in a new column. We'll call it in CI is going to be our new column name. We'll add that to our confidence interval data frame. Okay? All right, so now let's look at our CI's data frame here. And we can see that for the first sample, our lower and upper bound actually contain that population mean of 99.682, and we have true in the in CI column. And essentially that always works until we get to our 7th entry here. This was the first time we got a sample mean where the confidence interval generated did not contain the population mean, and we essentially had a false. And you can kind of leaf through the rest of the data here by going through. There's a lot of rows, but here's another example. All right, we see a false, and this identifies a case where now the confidence interval overshot. So it doesn't contain our population mean because the lower bound is too big. Right? So this in CI essentially is recording our whether or not that particular confidence interval, row by row, was successful. All right? So to generate, or to, to calculate our success rate, all we have to do in this case is look at our CI's data frame. We want to select the in CI variable. Right? This is a logical vector of trues and falses. And remember, if you sum a logical vector, it's going to count up only the trues. So the idea here is in this logical vector, when we sum it, it tells us that 2,848 of the entries in this logical vector were true. Now we know in general that the percentage of trues as opposed to the entire we can return by just taking CI's and finding the length of that total vector. Now we could just divide by 3,000. We know we collected 300 or 3,000, but we could also return this by just looking at the length of the logical vector, which is 3,000. And then generally speaking, just running this command, we end up with essentially about 95% of the confidence intervals we generated through this random sampling process actually contain the true population mean. And you'll notice that this 95% was exactly the confidence interval that I set above when I generated this margin of error. Okay? So this margin of error, which uses this z alpha over 2 term, is a finely tuned tool so that in the long-term repetition of this sampling and generating a confidence interval, you end up with a essentially 95% success rate. Which is all based on this underlying probability distribution for our x-bar. Okay, we're going to do another similar simulation example on Friday's class or during Friday's class. It'll be a little bit more complicated because we'll see that with the new confidence intervals, the sample standard deviation is also important. So we'll have to make some minor modifications, but this is the general idea. All right, thanks.